Yash and I are really excited to introduce to you an approach that we find really useful and exciting. So we think this is going to be the approach that's going to revolutionize our field. And of course, we are buyers. So we think, okay, why don't we just present it as it is, and then you will make your conclusions. But we do hope that you also see the value of doing things slightly differently, and you will let us know your feedback and your suggestions for us to improve it. So let me go ahead and share screen. Everybody can see it? Cool. All right. So in the ODC email, you saw the name was using AI to build theory. We were just using the buzzword AI. Actually, what we are using is the machine learning algorithms. So there is difference between these two concepts. If you are interested, maybe later Yash can elaborate on it. But let's go ahead and get it started. So today we will be doing this in 3 parts. The first part, I am going to walk you through our approach and explain why you should consider trying it. And later, Yash is going to come in with an illustration. It's a step-by-step guide of how to use it. And finally, we will do a group exercise, and also for you to see what you can do with the results. Let's start with this ultimate goal of scientific method. That is to discover the causal mechanisms underlying phenomena of interest. And in its essence, it is about observing facts and that help us to uncover the general laws governing the facts of a similar kind. And in action, I think the prime example comes from the history behind the theory of evolution. So after years of observation, Charles Darwin discovered this pattern. Despite their diverse forms, all species on Earth share the same origin. And his explanation of this pattern was that it is the natural selection process that accounts for the diversity in all these species. Then how does that relate to our work? Here I have the presentation art made by my colleague Marche. So suppose this is the real world. What is our goal as a social scientist? I know very often when we are working on our dissertation paper or working on R&R, we might forget what was the real reason or the ultimate goal for us to choose this profession. At least for me, that is to understand the world better, right? So how do you do that? There is this research process I stole from financial slides. And I think what is informed all of us, it is the idea and the process that's elaborated in Lavie and March's classic book. So we start with the real world and with the phenomena that we find interesting and we want to understand better. So with a set of data about that phenomenon, we could inductively derive a pattern. The next step is to construct a theory or an explanation to explain the pattern observed. Next, we could also deduct from the theory a set of testable implications and verify those implications and the theory using a different set of data. So this is a general research process. Our approach deals directly the starting part of the research process, that is deriving pattern from data and construct a theory to explain that pattern. And there are two core processes of theory building. Here is the induction and abduction, and we call them pattern detection and pattern explanation. Now, this is the process that we are primarily concerned about. Let's review what the traditional approaches have been. So in our field, theory building has traditionally been reserved for qualitative scholars dealing with a small sample of N. Here you see, I just gave the example, we have a small sample, then you can engage yourself in very deep qualitative analysis. Given your sample, then you can draw conclusion or derive explanation of the sample. So with this method, pattern detection and pattern explanation are intertwined and using the same sample. Here, my question for you is that, what do you see as the challenge? That when you want to develop a good theory, what are the challenges and what do you see as the biggest one? Here, let me launch a small poll. It's just, can you all see the poll? Some of you haven't voted yet. Okay. I just took a screenshot of it so we can talk about the results. I think our audience has overwhelmingly voted for all of the above. And I also saw some people have voted for none of the above. So that means there is one participant that thinks there's an additional challenge for theory building. Can you guys all see my screen? Right? So overfitting, there are 6 of you consider it as a very important challenge. And as I said, the majority has seen that the challenge is all of the above. Maybe let me quickly ask the person who has said it's none of the above, rather it is. Could you share what do you think is the additional challenge with us?
Hi there, this is Stunde Kletesh from Denmark. What I'm missing from a conversation related to AI and theory building is explicit discussion with the potential outcomes framework. So how the data generating process and the data you are working with affect the results, and not just comparisons to an associational statistical framework. So that's the thing that I was thinking about. Thank you so much for calling me out.
Sure. Yeah, thanks for sharing your perspective. Absolutely. I know for many of us, this using AI to generate theory sounds like a black box, and you would like to peek into the black box. So yes, with that in mind, today we are not just comparing the two perspectives, but we are going to look into our approach in detail. And here, what I wanted to learn from you through this poll is, what would you consider like the biggest obstacle for us if we want to develop a better approach to theory building? So here we can see that most of you think all this, so low reliability and human comprehension, overfitting, and predominantly overfitting is a very big concern, right? Because if we look back to the traditional methods, why overfitting is such a big concern is given the small sample and we don't know how the sample is constructed. Once we try to generalize the pattern detected here, very often we run into the problem that the population doesn't agree. Then the next question, if overfitting is such a big concern, why don't we just enlarge the sample size? Why don't we just do it with a larger N? Would that solve the problem then? I think from the audience response, we also learned that this challenge of human comprehension and also the reliability continue to be the concern here. If we have sample size of thousands or even hundreds, the pattern might very quickly exceed our bounded rationality. It might become very difficult for the human eye to discern the complex pattern here. The next concern is the reliability and the inter-subject reliability. So when you have different analysts looking at the same complex pattern, they might draw very different conclusions. And we don't have a good procedure yet to document the many steps of judgmental calls to make the entire process replicable and to compare the conclusions and the process of drawing conclusions done by different analysts. So with that in mind, we are trying to propose an approach that integrates machine learning algorithms for pattern detection. So we are not saying that machine learning will replace the human intelligence in the entire process, but we are suggesting that for the particular step, pattern detection, machine learning could be very useful. And more generally, we are proposing a new approach that we call algorithmic induction, and that has 4 steps. First, we would suggest for the researcher to split the sample into 2 random samples. Sample 1 is reserved for inductive analysis, whereas sample 2 is reserved for hypothesis testing. And in step 2, then it is where you could use machine learning algorithms for feature selection. So in this step, you do the pattern detection and identify variables that will be consistently predicting the target variable in sample 1. And step 3, that is the pattern explanation. That's when you develop a theory or process model explaining the relationships. Here is where the human intelligence or the researcher's sense-making comes in. And this is what we know as the theorizing part. And in step 2, that is when you will go to sample 2 to test the primary and corollary hypothesis to verify these out-of-sample and out-of-pattern predictions. And one thing to note is that Although we only use machine learning algorithms in step 2, the whole process, we consider the whole procedural and meta algorithm that can help you produce interpretable conclusions about robust patterns, and the patterns are likely to be replicable by other analysts and in other samples from the same population. Then the question, why algorithm? We think there are at least 3 advantages of incorporating machine learning algorithm here. The first one is that they can detect more complex patterns. I think this can be the least controversy point here. We know that machines can detect complex patterns, but why aren't we using them as much, at least in our field? I think it has to do with the fact and the distaste for prediction without explanation. So think about the many curious predictions you get from the Chinese fortune cookies. Do you have any faith in this prediction? So as a scientist, there is this natural distaste for prediction without explanation. If we don't understand it, we have very little faith in it, and we are very reluctant to use the prediction. But prediction without explanation could be helpful if the predictions are derived from robust stylized facts. That is to say that if the predictions are about the true patterns in the data, they could be very useful because they will serve as the input for your theorizing. A prime example is the robust association between smoking and lung cancer. Back then, when this association was discovered, people didn't understand it, but that is a robust association that later has inspired a lot of scientific research. And then there are different experiments and different type of empirical research and try to understand what this prediction is about. And there is a related debate, and also an additional advantage is using algorithms. Although they can detect very complex patterns, this complexity is also tunable. So when we face the trade-off of prediction versus comprehension, that we have that transparency and tunability to choose how complex we want our theory to be. The second advantage here is when you use this approach, it is an effective way to guard against overfitting, because the building features of machine learning algorithms, this regularization and cross-validation, they are very powerful guard against overfitting. So the patterns that you can find within your induction sample is a robust one. The final advantage is that these patterns also have a higher intersubject reliability. That means because of its algorithmic nature, there are ways that we can trace the decision-making point. So even if there are judgmental calls to be made, we know where to document it. And so to ensure that a different analyst could, with the same data, could come to very similar conclusion. But of course, we are not offering a panacea. It's not like if you use this approach, if you engage algorithms in the way that we propose, you have a panacea against bad theory. First of all, bad theory could be due to the spurious correlations, and the source of that spuriousness could come from omitted variables. That is not something that we can deal with. That still require techniques such as instrumental variables and ideally randomization. What we can do something about is the sampling error. So let's keep in mind that it's not all spurious correlations can be dealt with using our approach. And finally, our approach cannot guard against dishonesty. So this is an approach with the assumption that the researcher is honest and wants to understand the real world as it is and want to conduct honest research. So with this as my final note, I would hand over to Yash to walk us through the procedure.
Yeah. Could you stop sharing? Oh,
Mm-hmm.
thank you. Could you mute Vivianna? Sorry.
Yes, sorry.
Yeah. Okay. Okay. So what I will do is walk through our approach step by step, and also to understand our approach, I think we need a sort of background on machine learning and the algorithms that we use. So I'll start with the definition of machine learning, right? So we also know from last week, so machine learning is nothing but a computer program which basically learns from experience, which is basically the data from the past tasks, right? So it learns to do a specific task. So this task could be, for example, regression or classification for supervised machine learning. It could also be clustering for unsupervised machine learning. And for each task, there is a performance measure, right? For regression, you have like mean square error. For classification, you have a bunch of them like F1 score, precision recall, accuracy, etc. Right? So the idea behind building a machine learning algorithm is to build a program which learns from past experience to do a specific task, and the performance in the specific task is supposed to improve with a larger amount of experience. So in our approach, we use a specific kind of machine learning algorithm, which is a supervised learning algorithm. So supervised in the sense we have not only the features or the variables, but also target variables, that is a Y, right? So what we are supposed to do in supervised machine learning algorithm is to learn a model using both an X and a Y from the training data, such that that model can predict future Y for the future X, right? And so this learning step is not completely automatic. So it has a large number of decisions that as a human researcher, you have to take it. For example, you have to choose among a large number of machine learning algorithms that are available based on the amount of data you have, based on the task, and also based on amount of interpretability you want in your model. For example, deep learning algorithms, they perform very well with large amount of data, but they may not be interpretable. That means you cannot make sense out of the model you build, right? On the other hand, algorithm like decision tree, they are easier to interpret, and also it can it gives a good outcome even with a small amount of data. So based on the amount of data you have, and based on how much interpretability you want in your model, and also based on the task, you can choose algorithm, and then you train those algorithm in the training data and use it to predict in the testing data. And in the learning algorithm step, you also have a large number of techniques like regularization, cross-validation, etc., to keep a check on overfitting, to avoid the model fitting highly accurately on your training data and not producing good outcome on the testing data. So in the last week, our colleague presented this slide on like what are the different steps where you can use machine learning. So in our approach, we are also using machine learning in this step to induce patterns from observation and build theory. So we can also use machine learning to complement theory testing. And in the earliest slides, Vivianna also mentioned that we can use machine learning to also quantify some of the observations from the real world. For example, you can use deep learning algorithms such as facial expression detection to identify some emotions in videos or speech or images, and then you can quantify some variables from the real world and use that in your theory building exercise. However, we are particularly interested in this application in our approach to induce robust patterns from data and help use it to build theory. And also, machine learning has a large number of different applications. So in our approach, we will require the feature selection function of machine learning. So what is this? So basically, you have a large number of features, right, available. You want to reduce it to a small number of features. So basically, you want to remove the features that are not useful to you or that has lower predictive accuracy, and only keep those that have higher predictive power, right? So machine learning by definition is a prediction algorithm, and a naive way to do this is like you reduce one variable at a time from your predictive algorithm, and based on amount of reduction in your predictive accuracy, you decide whether you keep that variable in your important feature set or not. For example, if you reduce a variable x1, and if the predictive accuracy reduces a lot, that means that is an important variable, you want to keep it. If it does not reduce the predictive accuracy a lot, then you remove it because it is redundant for you. So that is a naive way to do it, but there are also specialized algorithms available to do it. So in our approach, we use random forest and lasso. So random forest is a ensemble method. So what it does is it builds a large number of decision trees using different subsets of the data and also different subsets of features that is available. And then it predicts using each decision tree, and it aggregates all those predictions to produce a final output. So basically using different subsamples of data and also different features, it produces an ensemble model. On the other hand, lasso is basically a regularized method where you are putting a penalty on the coefficients, right? So this is your regression loss, and with this lasso parameter, you want to make the loss higher if the coefficients are high. So basically, you are pushing the coefficients which are very small to become zero. So when you do that, you make some of the coefficients zero, and then you do feature selection. You remove some of the features from your model. So basically, we use these two models in our approach. And a critical difference between these two models is random forest, it is not interpretable at all, right? So you have a large set of decision trees, and it is difficult to interpret what is the logic behind the outcome. On the other hand, lasso gives you opportunity to explain your prediction, right? So because you have these betas, that gives you, how your variables are related to your outcome. At the same time, lasso, you can choose what is the degree of feature you want to have. What is the complexity of feature you want to have? For example, this action could be a monomial, or it could also be interaction term. You can choose what level of complexity you want to have in your model when you build it. So we will use these two in our approach. And so why do we do feature selection, right? So the one simple application is it makes training faster. If you have smaller number of features, the training is faster. But we are interested in the other two applications, regularization. So removing a redundant feature makes your a model less complex. And less complex models are difficult to overfit, right? So that is a classic bias variance trade-off. And another application of or benefit of feature selection is it helps us with interpretability. If you have a smaller number of features, the theory you induce, it is easier to interpret, right? So large number of features makes it difficult to interpret. And now with this background, we move step by step to our algorithmic induction approach. So let's start with a research question. For example, you are given this research question: what determines innovation outcome of a firm? Right. So this is a typical research question in management. And if you are given this research question, you start with collecting a large number of variables. Right. You start with collecting a dependent variable, the innovation outcome itself, right, which could be a continuous variable, for example, and then you create a set of other variables. It could be related to environment, for example, weakness of IP protection, advertising intensity, R&D intensity. It could also be related to some intrinsic characteristics of the firm, like the CEO, whether the CEO has appeared in Wall Street Journal or not, how much diversity is there in that firm, etc., right? So you have this outcome variable, and then you have explanatory variable, and you try to induce some patterns using your explanatory variables that explain your outcome. So we also have so we will take this research question as an example in our approach. So because in our approach we want to identify or evaluate the quality of prediction, quality of pattern we detect with reality, that is ground truth. And that is why we will do simulation, because simulation gives us this unique opportunity to know the ground truth, right? To know the reality, and then we will induce patterns in our data, and then we will compare that pattern with the reality, and then see how good or bad is our induced patterns. So we use a simple data generation process, which is basically a simple polynomial where our outcome, that is innovation outcome, is a function of a large number of 11 variables and some interaction terms and a Gaussian error with mean 0 and standard deviation 0.7. So basically the data looks like this. So we have our dependent variable, and there is a positive and significant relationship between weak IP protection and innovation outcome, and also R&D intensity and innovation outcome, and advertising intensity and innovation outcome. And there are several negative moderation effects. And we also create small negative correlation between two of our explanatory variables, that is weak IP protection and litigation intensity. So this is our goal. So this is our ground truth. And we want to see, we want to evaluate whether our approach will lead us to this reality or ground truth or not, right? So that is the objective. So as you see in our data, all our variables have mean 0 and standard deviation around 1, and except x11, all our variables are continuous, and x11 is binary. So let's recap the approach that Vivianna introduced earlier. So what we do in the first step is we split the sample into two parts: inductive sample and deductive sample. And we leave the sample 2 for later use, and we start with the inductive sample. We firstly use a set of machine learning algorithms to detect pattern in that sample, right? And then we will try to explain the patterns that we get from this step 2 in our step 3 using human intelligence, HI with capital H. And then we will use try to come up with two kind of patterns, out of sample and out of patterns, and then we will evaluate them in our second sample. So we will come to that later. Okay, so the first step is just a random split of the data you have, right? So the idea behind this is, try to reduce interdependency between the test and pattern detection, right? And we do a simple 50-50 split, but as a researcher, you can also choose to do 60-40, 70-30, depending on the amount of data you have, right? So that is possible. And then we work with this in our first step. So what we do with that data is now we run a random forest algorithm to reduce the number of variables from 11 to arbitrary number 5. So we can choose this based on the amount of variables you want to take to the next step. Based on your own interest and also based on how much error it will bring into the model if you reduce a lot of variables, right? So the choice is based on your own interest and as well as the predictive power, right? So random forest basically reduces the number of variables from 11 to 5. And we have to keep in mind that when reducing this variable from 11 to 5, random forest also takes into consideration nonlinear or interactive relationship between these variables. So it is not like simple linear reduction, but it also takes into consideration nonlinear relationship between the variables, because random forest, as we know, is an ensemble of decision tree, and every layer in the decision tree is a interaction, right? So if you have 3 layers, then you are taking care of 3 third degree interaction already. So basically, we reduce from 11 to 5 here. And now, after you have this smaller set of variables, you can decide what complexity of theory you want to build, right? Whether you want to build a theory to a level of degree 2, that is a polynomial, right? A degree 2 polynomial, which has like only square terms and interaction terms. You can also decide to go higher, right? Degree 3, degree 4, but it's rare to see degree 3, degree 4 uh, 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 relationships as a theory in our journals. So we decide to go only to degree 2 in our approach. So what you do here is now you build a polynomial, exhaustive polynomial of degree 2. So if you have 5 variables, you will have so you'll have 20 different terms in your polynomial. And then with lasso, you can reduce it to, for example, 7 variables, right? So again, 7 is an arbitrary choice. You can tune your lambda in your regularization to have a particular number of variables, right? So what we did in these 2 steps is like we started with 11 variables, and then we firstly reduced it to 5 with random forest, and then we made a choice of complexity. That is the tunable complexity, right? So we make a choice on the complexity based on what is the complexity of theory we want to build. So we selected only degree 2, and then after we select degree 2, we make exhaustive polynomial of degree 2 using those 5 variables. That gave us 20 terms. And now again with lasso, we reduced to 7. So basically, we now have these 7 terms, out of which 4 are monomial and rest 3 are interaction terms. So now we use this, and then we try to induce some patterns in our data. So what we do is simple OLS regression using those variables. So running OLS gives us some significant relationship that was there in the true data generation process also, right? So we see weakness of IP protection, advertising intensity, R&D intensity, all of them are positively and significantly related to our innovation outcome. We also see some significant negative interactions. Now we only take the significant terms and then we run another OLS regression on the same data, that is in induction sample. Then we have these patterns. So yeah, OLS gives us robust and interpretable patterns. We also check for the robustness of those patterns, on 10% subsamples. So basically, we we divide this sample into 10%, 10 subsamples of 10% each, and then we see that the patterns that was induced in the OLS is also visible, clearly visible in subsamples, right? And we can also do that with 80% bootstrap, for example, right? So in bootstrap also we see the same kind of patterns. So using these different methods, we can verify that the sample, the patterns that we induce are replicable across various subsamples and also various bootstrap samples. So that gives robustness to the patterns that we find. And once we have the patterns, and now we have to give it to the human intelligence to interpret it. So I give it to Vivianna to make sense out of it.
I get to be the HI only because my last name starts with H. So Yash was playing the AI role. So this is the pattern that we found. It's pretty complex, and I am not from the field. So let me just try to come up with the theory. It's also sometimes what we do on our field when we try to make sense of something. Let's imagine the process to explain this pattern. It's a theory about firms' strategic behavior and its institutional environment. If we just focus on the top level of the model, we can find the explanation as such. Okay, so there are two ways for the firms to boost their innovation outcome. One is to increase their own R&D intensity. Alternatively, it can try to capture the innovation that's already existing in its institutional environment. Let's think about the case of China. You can innovate yourself by increase R&D intensity within the firm or try to copy others outside the firm. And here we see there is a weak IP protection that has a positive impact on the innovation outcome, because if you try to, because that can make just copying or taking existing innovation outcome outside the firm easier. Then you also see litigation intensity has a negative moderation effect there. So if the litigation intensity is high, it's harder for the firm to capture to copy and capture the innovation outcome outside the firm and turn it into their own. So this is the explanation that I come up with. Then with this explanation, the next step is to derive implications of your theory that even you haven't seen that with the pattern that you found with your induction sample. So if my theory were true, this is a theory about how the institutional environment and the firm's strategic behavior are related to each other, then we would also expect firms are discouraged to litigate against others in the weak IP protection environment. So although we haven't seen that pattern in our inductive sample, but while abductively try to build the theory, we would have this as an out of pattern implication of our theory. That is the next step. We could actually try to verify if this implication is true, and then next, if our theory holds any validity.
Yeah, thank you, Vivianna, for the sense making. So now we have these patterns, right? These are the patterns that we induce from our machine learning and OLS algorithms, right? So the reason why we were able to identify this is because we use supervised algorithms. That means we have a very clearly defined target, right? So we have a target, and then we have a lot of features, and then we can derive all these patterns because all of them are directed towards a particular target. So we are not able to derive this from our approach because here a target is different, right? So the litigation intensity, this is a different target, right? So that's why this is out of sample, we have to test it out of sample, and this is out of pattern. So now we finally, with this in the explanation, we finally unleash the beast on the second sample, which was safe so far. And now we have this induced patterns, so, a couple of positive significant relationship to the DV, and also a set of negative correlations, right? So we test that in our, we unleash that, right, on our second sample, that is our out of sample prediction. And also the another explanation, there's a relationship between weakness of IP protection and litigation. We also test that in our second sample. So let's see what happens. So this is our out of pattern test. So we test that now in our second sample, and we see that we are able to identify all the significant coefficients exactly. At the same time, the coefficient value itself is not very far away from our ground truth, right? So the difference is very low. And so this shows that we identify all the out of identify all the patterns in our ground truth. And also, when we do a regression on litigation intensity, we can identify the out of pattern relationship also. So the in our ground truth, we have a negative correlation of -0.3. So we identify a positive significant correlation of -0.34. So with this, the combination of our induced patterns from ML and also the theoretically derived or sense making derived out of pattern, so we get almost all the relationship correctly. So the red one are the discovered, and the black one are the ground truth. Right. So yeah. So we saw from this approach that we are able to robustly and reliably identify all the relationship in our ground truth. Yeah. So should we take questions, or Vivianna, you want to go into this next phase?
We can take a few questions before we go into the exercise. If not, we can also go directly into the exercise. Yash, if you stop sharing, I would.
Yeah.
Good. Well, thanks, Yash, for walking us through the approach. I will go into a quick introduction of the recent applications of this approach. We were really happy to see this approach gaining traction, and more colleagues are joining us to try this different, what we consider a novel approach to build theory. I know Linux and his colleagues have been using this a similar approach to try to find robust patterns that so they also use feature selection and try to find the robust features that predict which ideas will take off at the Lego community. And then there are these MIT physicists, they use neural networks and try to recover the physical laws that they used to construct very big data sets, and they were able to recover all hundreds of physical laws in their exercise. And we also have seen other works using both pattern detection and pattern explanation. We are going to go into a little bit of the details of one such example because that's our own and we know it best. And I want to present just one most important pattern that we found in our exercise, and want you to put on the detective hat and to make sense of this pattern, try to construct your own theory and design the study to test this hypothesis. So this is the case for you to solve. It happened within the GitHub community. GitHub is the world's largest online platform for software development. I saw Matt here. Matt is a community member there, so you know what I'm talking about. It is not a utopia. There is conflict, and a particular type of conflict is very disruptive. That is what we call the governance-related dispute. One such example is the software license dispute. That is when these communities come together and develop software. First, they need to select a license for the product. But this is a very contentious decision, and often there is conflict around it. It's very hard to resolve because we know in these communities there is no formal authority. There is no boss there to call the shots and say that, okay, let's go this way. And in the GitHub communities, there is also no specific procedure that you can follow to resolve these conflicts. So we come in with the question, then how are these conflicts or disputes resolved in these communities then? Because we didn't really have an a priori theory that guide our exploration. We took this inductive approach. So we use 3 different combinations of algorithms on the data that we collected, and we found very surprising and robust pattern across all the algorithms. So let me just share with you. To simplify it, I just shared the most striking one. That is, we found the larger the discussion groups, the higher the likelihood for them to resolve a dispute. So take this as a robust pattern. How would you make sense of this pattern and construct a theory to explain it? Can you think of an out-of-pattern implication of your theory? And if you have time, design a study to test this hypothesis. So I would put you guys into 3 breakout rooms, and we have 15 minutes for you to work on this case. You can now take a screenshot, because once you go into the breakout room, you won't be able to see this screen. Oh, actually, we don't need to see my screen because I'm more interested in hearing your findings. What is your theory, hypothesis, and test? Who wants to start? We have 3 groups, right?
Maybe we can start with the smallest group because somehow I didn't see any other members in my group. That's why I had to ask for Coco's presence here. So we have 2 hypotheses to try to explain like why disputes are more likely to be resolved in larger versus smaller groups. So Coco proposed that like maybe in a larger group we have a larger diversity of ideas, so it's more likely to have like some common ground and people can find some ideas that they are more they can agree with. So this is one hypothesis. Another one could be in smaller group, creator can feel higher sense of ownership to the project, so it's harder to give up the baby to to give up the ideas and try to solve a problem as a group, as a community, rather than because there's some sense of personal attachment to the project.
Right. These are really good explanations, Donggi.
And we didn't really have time to develop a hypothesis, like test, design a study. Yes.
Okay, yeah, but good. You have 2 explanations. That's good, because a good social scientist should be able to come up with multiple explanations. Then you can have competing, right? Competing hypotheses. Yeah, that's really good. Thanks, Donggi. Okay, then next group. If we don't have volunteers, I'm gonna call Matt.
Okay, go on then. So our group were not necessarily, we did not converge on a study design or explicit hypotheses, but we thought that when you look at larger groups in this context, maybe the size of the group is actually representative of commitment. So one thing that you might have in, especially in that kind of context with smaller groups, is just that people don't care that much. So maybe this is a kind of omitted variable, right? And the other point that I think was important to us was related to creativity or diversity, that you get either a dampening in larger groups because of conformity bias, which is actually helpful in this context, or alternatively, just better solutions being proposed due to the larger size of the group.
These are excellent. So I say this is excellent with a little bit of pride because we thought about this too. And the first one you mentioned, size, is actually reflection of commitment. So there is an omitted variable there, right? And how can we check this? So we actually look into the size. So we are looking at the size of the discussion group, which are people involved in the dispute. But there is also the size of the entire project community. If it is a matter of commitment, then we should see the size of the project community having the same effect, right, on the resolution outcome. But we didn't. So we ruled that out. So that's not the commitment issue. And then there is also the conformity issue. That's also really important. We thought about that too. Then we say, okay, if it's a conformity issue, if we have the committee or what we call the administrator group, if the administration group is big, then they would have they can induce conformity, right? And we also didn't find that, so we ruled that out. Yeah, but these are very good. These are the the right place to look. These are the alternative explanations. Thanks, Matt. Okay, last group.
I'll volunteer to summarize what my group came up with. So
perfect, thanks.
It actually overlaps with some of the ideas of the previous groups. So one idea was that the larger groups are going to have more diversity of background information and knowledge about the task. So you're going to have more solutions proposed for decision alternatives. And then you're also going to be more likely to find at least a couple or one individual who has had prior experience resolving conflicts, so they know how to, they have better know-how about getting the group to process those alternatives and reach a solution, make a decision.
Awesome. Have your group thought about how to design a study to test this?
No.
No. Would be great if you have, because that your explanation cut very close to our own explanation. Yeah. So the information volume or diversity is part of our explanation of the process. So we were thinking larger group is able to garner the amount of non-overlapping information. That is one explanation. And the other one, you mentioned these key individuals who either had the experience of how to do it or just have that insight of how to turn the dispute process into something more likely to be resolved. And we call this individual reflective agency, not exactly because of experience, but because of some insight or instinct. They are doing that, but it's very similar in terms of the mechanism. So because in that study, we ended at the insight and explanation, we haven't designed any study to test this yet. So I was very interested in hearing what you have in mind, how the next study, the deductive part can be designed. Okay, but that's for future research. But thanks for sharing with us your theory. All right. So for those who are curious, what exactly is the theory? I would do some shameless self-promotion. This is the paper and the context of this exercise, if you are interested, that we have done the first part of the induction process. All right. So, so with that, I think my part of the presentation is done. We have about 10 minutes. We will leave that to questions.
Oh, firstly, maybe I'll show this slide on the regression. Yeah.
Right, exactly.
If you can stop sharing.
Mm-hmm.
Sure.
Hi, everyone. I had a quick question, and I'm sorry, my internet connection is terrible. I can't turn on my video. I was wondering, and I'm new to machine learning, so if the experts on the panel can speak about types of data, longitudinal versus cross-sectional, if there are specific choices we have to make as we navigate these different types of data sets.
So it's about the selection of data sets for running the machine learning part in the induction pattern detection part. Is that the question?
So let me think of a specific example. What I was thinking, let's say I have a longitudinal data where I have units observed over time. So when I'm splitting the sample, would you recommend that I look at some units or a combination of units in time? How do I split that? If I were to, like the 50-50, 70-30, 60-40, did you guys think about that or have any recommendations for that type of problem? And I can see Anish nodding his head. So, sorry, go ahead.
The principle might be stratified random sampling, right? So if your interest is in, if your theory is at the level of the unit on which you have multiple observations, you would put the entire unit's time series into one of the two buckets. So the random sampling is at the level of the units, right? But if your theory is more at the level of things that happen in a given year, then you could conceivably also cut it randomly at the level of years.
Got you. Okay.
Yeah.
So based on the theory, you will cut the data.
The rule of thumb of splitting is that the subsamples shouldn't be systematically different from each other. So you want to have the basically like identical twin when you create two subsamples.
So almost like a dyadic matching strategy, right? In some cases that we do, or the same philosophy.
Yeah, it's the same philosophy as randomization in general, right? So when you randomize into treatment and control, then the idea is they are statistically equivalent on everything except the treatment.
Got it.
This is the same sort of approach. Yeah, that's right.
Thank you.
Yash, please go ahead. I think you wanted to say something.
Oh, yeah. So I just wanted to show you how our approach is not a brute force regression, right? So we also evaluated our approach with brute force regression. So for example, if you do brute force regression with 11 variables, you will end up with 55 two-way interactions and 11 quadratic terms, right? And in total, you'll have 77 variables. And we ran a regression using those 77 variables on innovation outcome. So we were able to find those 6 terms that was in our ground truth. At the same time, we also found 4 additional false positives. So our algorithmic induction approach found all the 6 terms and no false positive, but this brute force gave us 6 false positives. And we also did stepwise regression, which is also common in our field. So that also gave us all the 6 terms in our data generation process, but also 4 additional false positives. So our approach was more efficient because we did not get any false positive. We got all the terms in the ground truth, but no false positive. But these 2 gave us 4 additional false positive. And also, there's a philosophical difference when it comes to the exploratory regression and our procedure. So in the first step, so it is not common to have a split sample method in the exploratory regression, but we do that because that protects us from overfitting, and also it avoids p-hacking, right? And also in the pattern detection step, right? So in exploratory regression, we are used to look for like p-values and r-square to check for model fit, and these terms there is a assumption behind that, right? So you start with the assumption on a particular relationship or a particular hypothesis. So because of that, you look for statistical inference, and p-values and r-square helps you to reach to that statistical inference. On the other hand, what we look for is robust patterns across different subsamples, across different bootstrap samples. So we are not looking for statistical inference, but we are looking for robust associations between different variables and the outcome. So that is why our process is different from typical exploratory regression. So just wanted to give that message. Yeah. Any questions?
There are a couple in the chat if you want to take them.
Nazar has a question about diffusion. Do you want to elaborate it yourself, Nazar?
Sure. So I'm interested in, for instance, how we can test the diffusion of, let's say, in interdisciplinarity. So there's ways to measure interdisciplinarity, and it has been established in the field on ways that they can measure it by diversity, disparity, balance. So there's, a multi-dimensional measurement for it. And I'm really interested to see how we can test the diffusion or the way that it propagates across, individuals who might work with, let's say, an interdisciplinary scholar and then tend to work on interdisciplinary publications as well. So I'm interested in the examination of the diffusion, like just as with biological studies, when they test the diffusion of a virus, and there's a specific measurement for that, the R0. I'm really interested to see if it is possible using machine learning, if we can come up with a measurement to see how an idea diffuses or how interdisciplinarity diffuses. So I hope you can answer my question.
So let me take that question. So I think one way of studying this is, collecting a large number of documents. This could be scientific papers or anything related to the idea or thing that is being dispersed, right? And using text analytical methods, you can compute variables such as cosine similarity, which gives you difference or the distance between 2 different textual documents, right? And then using those kind of variables, you can see what is the distance between one document versus another. And if you put all the documents that you have in a time axis, you can see the evolution of difference between the documents and also the evolution of similarity. So that is one way of classical way of measuring difference or similarity between the documents. But you can also come up with modern techniques like structural topic modeling, which actually gives you topic models for each document, at the same time evolution of topic models over time. And you can see whether there are topics which are floating from one document to another over time. So that could be a way to measure diffusion on text. Yeah.
Can we go though from an article level to a person level?
Yeah, so one way of doing that is firstly you create a network, right? So you can have a network of articles and person, and you kind of connect the article with the person, and then you can study diffusion in the people network based on the article network. I think that could be one way of doing it, because one article could have many people, right? Many co-authors, for example, and one people can have many articles over time. So you can have temporal evolution of that co-author network or scientific network, for example.
Great, thank you so much.
Thank you.
Okay, maybe I just add one little point to the question raised, which is that what Yash and Vivianna have been talking about is mostly around the detection of empirical regularities, not necessarily testing them, right? So if you actually have a theory of diffusion and you have a structure in mind, one could even just use a maximum likelihood or a regular hypothesis test to see if the parameters estimated in that model with the data, right, are consistent with some theoretical priors. But if, for instance, you wanted to see what predicts the adoption or the infection for a particular node in the network, and you have data on those nodes, then that's a classic induction problem. And then everything these guys talked about would be absolutely applicable there, right? So the simple way to think about it is that you see a pattern in the world, and it could be spurious because of omitted variables or spurious because of sampling error. This procedure that they showed you solves the second problem, right? That's all it does. It says the pattern you're seeing is real. It's not a figment of your imagination. It's not sampling error. You still now have to go through the entire process of figuring out why and testing if it's causal. But if we could do everything with algorithms, then we'd be out of a job. So great. I think we are at the end of the discussion time-wise. Thank you so much, Vivianna and Yash, for doing this. Really appreciate it. If you have a few minutes to stay back and people want to ask a few questions, is that okay? Can we do that?
Yes, of course. Maybe before we end the session, I have like a final closing remark to make is what we are proposing is not an advanced way to do p-hacking. Hacking or p-hacking. In our paper, we are running out of time, but in our Ox Science paper, we had a very detailed explanation. What is the difference? So I don't want you to walk away thinking about we are proposing an advanced way of doing hacking or p-hacking. It's quite the opposite. Yeah.
Thank you. That's important to get through. Thank you. Excellent. Thanks very much. And if you want to stay back and ask a few questions, please feel free. Otherwise, thanks for joining us. And we can turn the recording off now. Thank you.